to graph these out. So you need to be able to identify and do these kind of graphs. So let's do position versus time graph. Well, here's time, here's position. Well, position is a cosine. Cosine starts at 1 and goes down. Oh, that's not very great, but draw a cosine line like this, something like that. Oops, I don't know why that happened. And then when you look on here, you'll have a few things like the amplitude would be here. Amplitude, it's wherever you are at the max, and those two things would be equal. I didn't draw them very equal, but that's your amplitude. Your period, which is the amount of time that it takes to repeat a cycle, would be like from here to here. This would be the period, t. We've got that right there, period. Period could also be measured here, where it's going down, over to here, where it's going down. Not here, because there it's going up, and it's from the same place to the same place. One full cycle, that's also the period, things like that. We could go back and draw in, now do a velocity versus time graph. Velocity versus time, notice, is negative of sine. So it would be a sine graph. Sine graphs normally start and go up, but this one's negative, so it's going to start and go down. And then it's going to, sorry, you want to try and match these up where, I should have drawn these over top of each other, but I didn't, because like when this is at a max, this is at a min. When this is at this here point, I should do that. Let me just do that. I'm going to put it right below it. I'm going to try and match it up. So try and match up these kind of points. Go straight down, straight down. I'll see if I can do this pretty well. It's kind of hard to draw. So here, this is at a maximum, this is at 0. So then this is going to go down, and when this is at a maximum, this is at 0. And then this is going to curve up to 0, and when this is at 0, this is at a maximum. So you get that kind of just slightly off pi over 2 phase difference, right? Cosine of, pi over 2 is the same thing as sine of 0, or sine, or what am I saying? I'm saying that like cosine of theta plus pi over 2 is equal to sine of theta. It's that phase shift, right? If I add pi over 2 to cosine, I'm going to get what the sine of the angle was. Like cosine of pi over 2 of 0 plus pi over 2 is equal to cosine equal to sine of 0. Alright, so this is velocity versus time, and then I'll try and get this third one in here. If I could get this last one in here, I'm going to have to kind of squish it down to keep them all on here at the same time. But keeping these same lines going, if we look at this next one, acceleration versus time, it's back to being a cosine graph, but a negative cosine graph. So when this is at a maximum, this is down here at a negative maximum. When this is at 0, this is also at 0, and when this is at a maximum point here, this guy's gonna, I'm sorry, when this is at a negative maximum, this one will be at a positive maximum, and so on and so forth. It'll go on like that. It like mirror images this one. Okay, so I'm sorry my drawings aren't that great here, but basically that's what happens. These are slightly out of phase with each other. These two are just inverses of each other that can be scaled a little bit. Talking about them even scaled, they have different units, so it's hard to compare how tall they are to each other. That we can ignore. I started drawing it and shouldn't have, but that's the basic graphs of them and how they relate to each other. You need to know that. So when you go through, excuse me, when you go through simple harmonic motion, you can look at different parts of it. So for simple harmonic motion, we can make this kind of chart here, which we should be able to basically, you don't have to memorize this chart, you should be able to just kind of figure it out by thinking about what's happening. So first off, simple harmonic motion, when displacement is at a maximum, what are we going to have? We're going to have a position, we're going to have a velocity, we're going to have a time, we're even going to have a kinetic energy and a potential energy here. Okay, so at maximum displacement, we can look at each of these things and kind of make ourselves a little chart here. So at maximum displacement, X max, this is obviously a maximum, right? What about velocity? Velocity at maximum displacement, it's 0. Because if you look here, we're at maximum displacement here, and velocity is 0, which makes sense because as this thing travels back and forth, it's going to the right, it's going to the right, slows down, slows down, slows down, and in order for it to start going back left, it has to actually come to a stop before it can start going back left, and before it can start going back to the right, it has to come to a stop and start going back to the right. Okay, it's kind of like at the highest point, you throw a ball up in the air. At its highest point, it's going up, 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 up. In order for it to start coming back down, its velocity has to reach 0 before it can start coming back down. So the velocity is 0 at that point. So, just thinking about that, here it is. I mean, even think about Hooke's law, F equals negative kx. What happens is we start over here. As it starts to go towards equilibrium, x decreases, so the force decreases. But the force is pulling it to the left, so it speeds up, speeds up, speeds up, speeds up, slows down. But as soon as it crosses equilibrium, its displacement is now to the left, which means the force is now pointed to the right. So it starts to slow down, slow down, slow down, slow down, stop, starts to speed up, speed up, speed up, because now the force is still pointed to the right. Speeds up, speeds up, speeds up, speeds up. Now suddenly the force is 0 here, and then the force is pointed to the left. Its momentum carries it past the equilibrium. And so it starts to slow down because now it's moving to the right and the force is to the left. So it slows down, slows down, slows down, stops. Now it starts to move to the left and the force is to the left, so it speeds up, speeds up, speeds up. Force is 0. Now force is in the opposite direction, so it slows down, slows down, slows down, stops, speeds up, speeds up, speeds up, and it goes back and forth. That's what it's doing, right? So just by thinking of that or looking at the graphs, we should figure this out. I didn't mean to write time. I meant to write acceleration there. Sorry. When we are at a maximum displacement, x is at its biggest, so the force is at its biggest, so therefore the acceleration is at its biggest. So this is either, this could be, I should write this is acceleration or force, because remember acceleration and force are always related, they're just scaled by each other, so force, maybe I won't write a slash, it'll look like divided by force, I'll just write the word force or and acceleration. How about that? They're maximums. If x is a max, force and acceleration are max. They're proportional to each other. What about kinetic energy? Well, we'll look at kinetic energy. Kinetic energy is about velocity. Velocity is 0. Kinetic energy is 0. Potential energy is based on position. We had potential energy for a spring. It was PE equals 1/2 kx squared. So potential energy is a maximum when displacement from equilibrium is a maximum. So this is a maximum here. What about at equilibrium? At equilibrium, what do we have? At equilibrium, that's when x is 0, so this is 0, right? So this would be equilibrium right here, when x is 0. When x is 0, if you look down here, velocity is at a maximum, which also makes sense because as it heads towards equilibrium, it's being accelerated faster and faster and faster. So on its way towards equilibrium, it's speeding up. As soon as it starts to go away from equilibrium, it starts to slow down. So where's its maximum? It's right there. It's where it's had the most amount of time to speed up, and then immediately after that, it starts slowing down. So that's going to be your maximum, and it's shown here with our my wonderfully perfectly drawn graphs of the motion, velocity, and acceleration. Force and acceleration. Well, if x is 0, force is 0. So there's no force there. Momentum carries it on by. Kinetic energy is based on velocity, so this would be a max here. And then potential energy, again, is based on x. It's going to be a 0 there. Okay? So that's our little chart. Anything in between. We're not at a maximum displacement. We're not at equilibrium. These aren't going to be maximums. This is going to be greater than 0. This is going to be less than maximum. This is going to be greater than 0. This is going to be less than maximum. It'll be between these values. This is just where it's maximums and minimums. Okay? So I've already shown you how this can relate to how this equations here give us waves as well by pulling our piece of paper underneath our spring bouncing back and forth. Gives us that wave motion. So this mathematically can describe waves just as well as simple harmonic motion, which makes waves a form of simple harmonic motion. And we'll take advantage of that in the future when we really get into waves more than just simple harmonic motion. But this can also relate to circular motion. So imagine we have a ball going in circular motion, right? Constant circular motion, just going around and around and around this circular motion, right? And let's imagine we have a light source over here. We're shining light on it. And over here, we have a wall. And on this wall, we can see the shadow of the ball. As the ball moves down, the shadow moves down. As the ball gets here, the shadow gets here. As the ball goes here, the shadow goes here. As the ball gets here, the shadow goes here. As the ball goes back up, the shadow goes back up. Right? And as the shadow goes up, it goes up, reaches a maximum point up here, stops, and then it'll just cycle. So as this ball goes around, our shadow just goes up and down. And as it goes up and down, you can imagine right here, the ball's moving the fastest in projection because it's going straight up and down. Here it's kind of going at an angle. So its velocity is like this, which means it has a downward component and a horizontal component. Well, the shadow doesn't show this horizontal component, so all we get is this smaller downward component. So the shadow's not moving as fast here as it is here, where all the velocity is straight down. There's no horizontal component. And the same thing here. There's a horizontal component and a downward component, and we only see the downward component in the shadow. So it's slower here and here than it is in the middle. So fastest in the middle, slows down out here, comes to a stop down here for a moment before it starts going back up. Looks to me like this shadow fits simple harmonic motion. So the projected motion of the projection of circular motion onto something flat, onto a one-dimensional surface like this, is also simple harmonic motion. So the motion of the shadow of the shadow is simple harmonic motion. So circular motion can be projected into simple harmonic motion, which means this also is very strongly mathematically related and mathematically a foundation for circular motion, and we'll take advantage of that later as well. So now let's do one last thing. Let's just do some examples of simple harmonic motion. The first we did was the mass spring system, and if there's no mass spring system, that was that one I used above, spring system, the one I used above there, if there's no friction, sorry, I really need to work on my handwriting on this. I thought I'd get better, but it hasn't. Then this is simple harmonic motion. So with no friction, this equals simple harmonic motion. What about something like a bouncing ball? Is that simple harmonic motion? Well, this one we already talked about, we know it is. Well, what does it do? We have a ball, it's up here, goes down, hits the ground, bounces back up. So it's repetitive motion, it's going back and forth. When it's up in the air, the force is pulling it back down. What would we define as our equilibrium? Like maybe the ground is the equilibrium, right? So maybe that could be our equilibrium, where we get down there and it swaps the other way. So always when it's away from equilibrium, the force on it is back down. It's repeating the same motion over and over again. So is this simple harmonic motion? Well, if you look at just that part, it looks like it. But does it fit Hooke's law completely? Hooke's law says that F has to be proportional to negative of displacement. And if we go based on what we know for the force of gravity, F is its weight equals mg. There's nothing in here about how high it is off the ground, which means that close to Earth's surface, it's not inversely proportional to the displacement. So as you get up high away from the ground, it's not getting stronger. In fact, here, the further you get away from equilibrium, the stronger the force gets. Here, if we go into full on, which we haven't learned yet, it looks like this: G m1 m2 over r squared. R squared is how far away you are from the planet. It's on the bottom. It actually gets weaker, which I think you should know about gravity. You should know by this point in your life that the further you get away from objects, the weaker gravity actually gets. This is just our this here version was just our close to Earth's surface approximation. So a bouncing ball, not simple harmonic motion. Don't make the mistake of thinking it is, because the force here is not proportional to how far away it gets from the ground. It's actually inversely proportional to the square of how far it gets away. So that one's definitely not. This one is. What about a pendulum? right? Pendulum, basically attach a string to something or a rod, and you pull it off to the side, right? It's attached to something here, and you let it swing back and forth, right? Swings back and forth, and then has its straight down point here, and it'll swing back and forth. So this is repetitive motion. This would definitely be the equilibrium. It goes up to a maximum, slows down, stops, starts going the other way, reaches fastest speed down here, like swinging on a swing set, slows down, stops, comes back. Sure seems to fit it. So let's look at the restoring force that's on there. If we look at this, this is the force, mg. The part of the force that we're interested in is restoring this way. I'm going to let you do the triangle on this. We have two components, one that points this way, one that points this way, that's perpendicular to the direction it's headed back towards equilibrium. And it turns out that if this is theta, this is mg sine theta. You do the geometry of that, figure out what theta is and where it goes down here, and you'll get mg sine theta for this component here, right, where this is the right angle. So our restoring force here for the pendulum question, maybe I'll write it over here, is F is equal to, and again, we're going to put a negative there because when it's off to the left, that's pointed to the right, and when this is off to the right, it'd be pointed to the left, is equal to negative mg. I mean, we could absorb the negative inside g, but mg sine theta. So m and g are constants near Earth's surface. We have a negative sign, but look at sine of theta. Sine of theta is not just plain x. So this is technically not simple harmonic motion. Right? It looks very much like it. Well, the reason it looks very much like it is because what we can do is something called a small angle approximation. And you can try this. Put your calculator into degrees and do the sine of something like 0.01, and then and you'll get an answer that's almost 0.01. So basically the small angle approximation says that if you're in radians, the sine of theta is approximately equal to theta. Okay, it's approximately equal to theta, in which case F would become negative mg theta, approximately, for a small angle, right? Small angle approximation. We call this the simple pendulum because solving it with the theta in it, the sine of theta in it, is really difficult. Doing this approximation for small angles, great. How small of an angle? I don't know. The smaller the angle, the better this fits. It just depends how accurate do you need to be for how far away from actually being a small angle you can get. It really just depends on the application for how accurate you have to be. But basically, F is equal to negative mg theta, and now suddenly look at this. This looks like Hooke's law. Negative, constant, and then theta is our angular version of displacement. In fact, if you are in radians, theta is directly proportional. If you measure this in radians, not degrees, then in radians, the displacement here, arc length, how far along a circle you are, is equal to, so arc length, or what would be x in our case, is equal to r, the radius of your circular path, r, which would be the length of our pendulum, times theta. So this would be ma is equal to negative mg theta. The m's would cancel. G theta, we can replace theta by multiplying both sides by the length of our pendulum, or the length of our pendulum L. So we get LA equals negative G L theta, right? But that gives us this, then just becomes a distance, right? So this would be A is negative G over L times our arc length x. So now we're back to this whole exact Hooke's law, but with G over L instead of M over K. Okay? Oh, there is one thing I didn't point out up above. Up above, when we had M over K, we had this omega. I'm sorry, I totally forgot to do this and I just realized it. What is omega? Well, look, omega's right here, omega here. This is the one that fits our Hooke's law, right? A equals negative some constant k over m equals x. A equals negative A omega A times cosine omega t is our x. What's the little constant? Omega squared. So that tells us that omega squared, the angular velocity, is negative k over m. I'm sorry, not negative k over, just k over m, because the negative's right there. And so omega equals square root of k over m, which means we can write these out. As other. Basically, you can replace this with just square root of k over m into it. Okay, and then if this is omega, right? Well, what's the relationship between angular frequency and regular frequency? This is an important one. It's omega equals 2 pi f. That's a big one to remember. This is regular frequency, cycles per second. This is radians per second. And you imagine if you multiply 2 pi times your cycles, you're going to basically convert it into radians. So this 2 pi basically just converts cycles into radians. Okay, so that's where this relationship is. It's really just a unit conversion. But if that's the case, that tells us that 2 pi f equals square root of k over m, which means that frequency for simple harmonic motion, or a mass spring system specifically, is 1 over 2 pi times the square root of k over m. And then period, so that's a big one right there, period is equal to the reciprocal of that, so 2 pi times the square root of m over k. I'm very sorry I forgot to do this earlier, because I was just about to do it with the other one, and we've got that. If we go down to our other one, we can work out a very similar relationship. These same equations are going to be solutions to it again, but this time down here, we'll have omega equals g over L, and that gives us 2 pi f is equal to g over L, not g over L, square root of g over L, because it's omega squared. Sorry, it was omega squared equals g over L, because it's the exact same thing that I had up here, right? Omega squared is equal to the constant's g over L, so it's omega equals square root of g over L, right, from right here. Because these same solutions work for it, because it's the exact same form, just a different constant right here, right? Same form, different constant out in front. This is our Hooke's law here. And we get 2 pi f, so f for a pendulum is, square root there, is 2 pi times the square root of g over L, and the period, which is the reciprocal of that, is 1 over 2 pi times the square root of L over g. What do you notice is missing from this pendulum equations about how quickly it takes the pendulum to go back and forth, the frequencies and the periods? The mass. The mass at the end of the pendulum is missing. The only two things that determine how quickly a pendulum swings back and forth with the small angle approximation is the length of the pendulum. The longer that pendulum gets, the longer the frequency gets. The longer the period gets. So the longer the pendulum, the longer it takes it to swing back and forth. And then what planet you're on, right? The bigger the force of gravity, right? The bigger this number on the bottom gets, it does the opposite. So look here. The bigger the force of gravity is, the bigger your frequency gets. It swings faster, which should make sense, because a falling object on the moon is going to fall more slowly than an object on Earth, and so this is basically it falling back and forth, right? So it means if you had a grandfather clock that keeps time by tracking how long it takes a pendulum to go back and forth, like every time it swings, tick, tock, it's a second. If you took that grandfather clock to the moon, where g would be less, your clock would run slow. This number would get smaller, that makes the period bigger, it makes it take longer to swing back and forth. So instead of swinging back and forth and counting proper time, your clock's gonna slow down as the pendulum slows down. Also notice another thing missing from here, not just mass, but the actual angle itself is not in here. So it doesn't matter. If I take a pendulum and let it swing in a little arc, it's going to swing slowly in a little arc and take just as long to go back and forth as if I do a bigger thing. It's going to swing faster, but it has a bigger distance to swing through, so the overall time it takes to make the full swing is the same whether it's a little swing or a big swing. Little slow swing over a small distance or big fast swing over a big distance. Same amount of time. Okay? That's just a couple interesting things about it. So make sure you know this. Make sure you know these, and I'm sorry I forgot to give that to you up above. Hopefully you don't have to watch this video too many times to kind of keep up with what I'm saying. I feel like I just really did tell you quite a lot right there, but I feel like it's the necessary introduction to make sure you understand everything else that we're going to do. All right? Thanks very much, and I think that's about all. Just realized I forgot something in the last little video there, so I'm going to add it on the end. I didn't actually talk about the energies associated with simple harmonic motion. So just real quick, simple harmonic motion energies. Basically, if we track this energy through time, and we can keep going longer and longer, we'll have the total energy, which will remain constant. Assuming there's no friction or anything in here, what we'll have is total energy, just going to stay constant. That's conservation of energy. So that's total, basically total mechanical energy, assuming no friction again. Well, we're going to start with the situations like we looked at. We start with potential energy, right? Because we have our little mass on a spring here, right? And here's equilibrium. Say here's equilibrium, so we stretch it out here to the amplitude, the maximum it's going to be, and then we let it go. Well, at this point, the velocity is 0, so the kinetic energy is 0, right? But we have all potential energy. So the potential energy is going to be at a maximum here, and then as this thing goes towards equilibrium, this potential energy is going to drop down to 0. Okay, that's supposed to be a little bit more of a nicer little like curve. Oops, still doing it again. And then as it passes equilibrium, it's going to start to compress, 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 and it's going to gain back potential energy. So it's going to do something like that. And if we wanted, it would just keep on doing that, down and up, like a sine wave. Okay? And then what happens to the kinetic energy, right? This is potential energy. Well, the kinetic energy is going to do the exact opposite. The kinetic energy is going to start at 0 because it's not moving out here, and then it speeds up, and reaches its fastest point here. So the kinetic energy is going to go up and reach a maximum here, right when the potential energy is at 0. And then as it passes here, it's going to start to slow back down until it stops and goes to 0. So it'll come back down. Sorry, this is supposed to look like a sine kind of curve. And it'll come back down and stop, and then of course it'll just keep going like that. And they keep alternating. That's your kinetic energy. And then if you add these two up, every place you go, they add up to this total mechanical energy, the total energy just staying a constant as you go through. So here it's 0, this equals, here they're both half of it, they add up to it. So everywhere you go, we add this to that, and we get the total. And it just keeps going like that. All right, that was it.